So far in our study of integrals, we have only dealt with positive functions. In other words, functions that were above the x-axis. And for that, the area was exactly equal to the integral from a to b. However, graphs certainly do go below the axis. That's totally reasonable. And the question is, do we have the same relationship at this point? Well, again, this is where we go back to our definitions. If we're talking about an integral that's coming from a Riemann sum, and remember those Riemann sums are built out of the function values. Specifically, if we were building a rectangle here, we'd have a positive rectangle. And then when we get to negative values, maybe rectangle area isn't the best analogy, because here we'd have our f of xi negative. We can still take this combination. We can still take the function value times delta x, but it's a little dodgy to call it area because we'd be talking about negative quantities. The nice thing about this, if we look at these pictures, is that it's very obvious when we have a graph which of these areas are going to represent positive contributions to an integral. Anything above the axis is going to be adding to the total. Again, thinking of the sum of f of xi's times delta x's, these are all going to be positive on A, C, and E. Of course, when we have negative values for our function, we would have subtracting effects in our integral or in our sums, and that's going to be on B and D on the sketch that we have here. So here we see a bit of a breakdown between the area as in the integral and the integral with negative quantities. Integrals can have negative quantities. So if we now express this integral, so take the whole function, here it is, and it's all relative to the x-axis here, y equals 0 line here, t-axis technically, we're using t as our variable. And if we were to add these things up, thinking again of the analogy of the Riemann sum, if we were to add up the function value at each point times a little delta x, what would we get as the net sum of that? Take a look at these values, and remembering that when we talk about areas, areas are always positive. We'll never say -3 square meters. So areas are always positive, but we might subtract them from something else, and that's a legitimate way to phrase the sentences. So take a moment to ask yourself, how would we calculate this integral if we knew the areas A, B, C, D, and E? We'll check back in a minute. All right, so in A, C, and E, we would have positive values for our function. And then for B and D, we'd have negative values, and those would essentially subtract away from the total of the integral. So the integral will have positive contributors and negative, and those will cancel each other out to the extent that the areas cancel out. And so what that means is we're going to end up with positive contributions for A, C, and E. And notice the negative sign in front of the B and D here. That is going to be our integral value. That can feel a little counterintuitive. Let's try to bring it back to something physical and see if that helps, if this is not immediately obvious. If we now think of this graph as a graph of velocity against time, think about that for a moment. Ask yourself, what does it mean on the intervals B and D to have a velocity that looks like that? This is a perfectly reasonable velocity graph, but what would it correspond to in terms of physical meaning? Think about that for a moment, then we'll check back in. All right. Well, let's start with the A. B and D are the new things. We'll start with A. This integral under the velocity graph we found earlier, in fact, this is our starting point, represent the distance traveled. Now, if we define an axis and say this is position, x, and this is 0, this would be positive or forward motion. So the larger this area is, the larger is the distance that we will have traveled forward on that time interval. We know, in other words, the higher the velocity and the longer we're traveling, the further we're going to go. Well, that means there's a nice simple analogy here. When we're in the negative velocity territory, we're going to have negative velocity means moving backwards. We're backing up. And so if you want to talk about the integral being total distance traveled, we move forward for a bit, and then we stop, velocity 0, and then we're going to move backwards for a little bit. Now, you have to be a little bit careful here. The areas below the graph represent the distance traveled again, but it is going to be the distance traveled backwards. Just a sign difference from the distance traveled forwards on each of the regions that have positive velocity. B and D represent negative velocities, which are motion in the other direction or motion backwards. And so we still have that analogy that the area corresponds to a distance traveled. It's just the sign of that interpretation that we change. That is now distance traveled backwards. Again, that can take a bit of getting used to. Definitely explore the practice problems to see if that helps to clarify some of the concepts and the relationship between what we usually call areas and what we're now calling the integral value.